deriving the equations for the UR5 manipulator. So this is a figure of the UR5 manipulator with the axis, body frame axis shown. Okay, so 6 links, 6 joints, which means that there'll be 6 equations of motion. So the equations will look this: M Q Q double dot plus C Q Q dot plus G Q G equals let's put torque, and Q is a real number, it'll be at 6 dimensional. This just means that Q belongs to a set of real numbers of which has 6. It's basically a vector of 6 dimensions. Okay. Same for C and G. And then M is a matrix, so you write it as 6 cross 6. Okay, so how do we derive the equations? Well, if you use Euler-Lagrange equations, this is just symbolic. It'll be lengthy. Also, you'll see that if you try to do this with the Python symbolic package, it could actually just be calculating for a long time, and you don't want that to happen. You could use Newton-Euler, same symbolic. It'll have the same problem. It'll be very lengthy because you're trying to do symbolic calculations. So what we'll do here is we'll use recursive Newton-Euler algorithm, also known as RNEA, and we'll use this in a numerical fashion. So how do we do that? Well, I wrote down the general method. There are equations for force and torque balance. You take a single link. This link is ith link. It's connected to the I-1, I+1 link. You can write the force equilibrium, which comes from Newton's second law. The torque equilibrium or torque balance, which comes from the second law, but for the rotational counterpart, that's written down there. So that will give you just the force and torque. But if you look at the force and torque, it depends on things like the angular acceleration, also the linear acceleration, angular velocity, and so on. And so you need to figure out the velocities. So you can also write equations for the linear and angular velocity, linear and angular acceleration of that single link. The top one is for the revolute joint, the bottom one is the prismatic joint. So you have kinematics, which is these equations, and then you have the dynamics, which are the equations I just showed. How do we put it all together? Well, you have to do 2 recursions, a forward recursion for velocity and acceleration. So you start from the base link, which has 0 speed, 0 acceleration, and then you go forward, propagating using the equation in the forward direction to get the velocities and angular velocities of all links. Once you get that, you need to go through a backward recursion for forces and torque. Start with the last link. You show that the last link is 0, and you work your way backwards to get the forces and torques at each link. Now, eventually, the equations of motion will be sitting in the torque terms for a manipulator, for a revolute joint. For a prismatic joint, it'll sit in the force terms, which will be in this thing, not in the torque. And you could also have a combination, like when be doing a quadruped, sits in force and torque. Okay, so I use this for the planar manipulator. You can do the same thing for the UR5. So we did this for that manipulator. We'll do it for UR5. Instead of doing it here in class, I just wrote the equations. I'll show you what they look like. Okay, so in the main file, if I want to use RNEA, that is the recursive Newton-Euler, I need two things. I need to specify the joint angles, which is q, and joint velocities, which is u. And the function is expected to return the Coriolis term c, the gravity terms g, the sum of the two, which is packed together in CG. That way I can use it. And then we can check that against MuJoCo. So RNEA accepts q and u as inputs. It's actually sitting right here. And then it basically computes CG and Q. Now, before I compute CG and Q, this is just showing the forward and backward recursion. The forward and backward recursion is the same formulas I wrote down here. So that's the forward recursion for velocities, backward recursion for forces and torques. So what this does is it computes the velocities first. So it does the forward recursion first. You can only do the forward first. You can't do the backward because the torque balance relies on velocities and angular velocities and accelerations. So then I do this to compute all the velocities. So omega is w, linear velocity is v, omega dot is acceleration, v dot is linear acceleration, and the v dot c is the linear acceleration of the center of mass. Okay, all that now goes into the backward recursion, which is starts with the force of 0 and torque of 0, work your way backwards through the formula right here. So this you can see the force at link. Well, this is just the inertial force Fn, which depends on the inertia and the mass. No, sorry, uppercase F is the one which depends on the mass, and uppercase N depends on the angular velocity, angular acceleration, and the inertia. And then this is basically the recursion. So all these terms have been defined here, and basically that formula which I showed. Okay, so we did the backward recursion. What comes out of it is the torques. The torques are written in this variable called n, and I just pluck out the torques by looking at the axis, the joint axis. So wherever the joint axes are, that is the torque I need to figure out, because remember that the axis define the direction along which this manipulator will rotate, and that's where the torque is going to sit. Okay, so that's just that function which does forward backward. I need to actually call that repeatedly. The way I need to do this is by exploiting the fact that the equations look like this: m q q double dot c q q dot plus g q comma g. Compute m numerically. What I need to do is this is what the equations looks like with a 3 degree of freedom manipulator, which I showed, but this will be 6 numbers here. So I send in 1 0 0 in that forward backward recursion, and that will actually give me, and of course put q dot is 0 and g equals 0, so that terms cancel off. So I did it here, and then what comes out for torque is the first column of the mass matrix. And then I can do the same thing by putting q2 dot equals 1 and the other thing 0. Of course, q and g is still 0, and I get the second column, and then you can do the third column. So here, for the planar manipulator for 3 degrees of freedom, I need to do 3 calls to this forward backward recursion block to get the value of the mass matrix. For a 6 degree of freedom manipulator, it will be 6 calls by putting each of those accelerations to 1. Then I need to compute c and g, and the way I compute c and g is I have it earlier. All you need to do is to compute c. We note that c is only a function of q and q dot. So q dot actually explicitly comes in this equation in such a way that if you put q dot equals 0, this whole thing cancels off. So one way of writing this equation is cq q dot times q dot, where how books write it. I just wrote it this way, but note that this disappears when q dot is 0. So I can essentially get g by putting q dot equal to 0, q double dot equal to 0, that'll give me g. And to compute c, I can put q double dot equal to 0, and then put q dot equal to 0 to get g, right? So C and G are computed. Okay, so the code here essentially does that. It computes C by putting, in this case, G equals 0, and also the acceleration equal to 0. Okay, then I compute CG by just putting Q double dot equal to 0. So it's a sum of C and G. So this is another way to do it instead of trying to compute G individually, but you could compute G now by just doing CG minus C, because this is going to be the sum of C and G. And for the mass matrix, that's just a mess because I need to do it 6 times, 6 calls. This NV is basically the dimensions of the manipulator. So you do 6 times and you get each of those columns and put it all together. So when I run this, I'll get these values, but then I can compare against MuJoCo. MuJoCo has this QFRC bias, which gives me the C plus G. So it doesn't give you C or G independently, but it gives you CG. So what I did was I printed that out as MJ. Then I printed my value as pi, CG pi. I compared the difference, easier to look at that, should be all close to 0 or 0 ideally. Then I compute the mass matrix. For that, you need to use the function MJ full M. And then I printed the mass matrix in the using MuJoCo, using Python, my code, and then I do the difference, which should be close to 0. So let's run this and see if we can get the data. And I just did it for a few seconds for a particular value for Q and U, which is the position and velocity of the joints. Okay, so here is what I get. This is let's look at the easier one, CG. This will be a 6x1. So this is CG computed by MuJoCo, CG computed by pi. The difference is easiest to see. It should be all 0. So it's close to 0, but not quite 0. But I think I'm happy with this, with the difference being so close to 0, not exactly 0. And then the mass matrix is 6x6. My computation, the difference being also very close to 0. Okay, flag. Okay, I should do this way. So I should run this now, and then we'll see the time. So it all computes fine. M pi is not zeros. Here is the time. Okay, this is what I expected. It's 11.4 milliseconds. Okay, and this is done repeatedly. So sometimes it'll be fast, sometimes it'll be slow, but it'll be in the ballpark of about 10 milliseconds. Yeah. So is 10 milliseconds bad? Well, it turns out that some of these controllers will run at 1 kilohertz or 1 millisecond. So we need this to be done faster than 10 milliseconds. Now, of course, one way is to switch from Python to C, and then your problems will go away. But really, we want to find better ways of computing one specific thing, that is the mass matrix. In fact, if you put 0 over here, which is basically now going to skip computation of the mass matrix, you see that the time reduces from about 10, 11 milliseconds to almost, how much? 0.002 milliseconds, right? So the 5 times speed up you get because you did not compute the mass matrix. So 2 milliseconds if you don't compute the mass matrix, 10 milliseconds if you compute the mass matrix. And why it's so expensive is because you did 6 calls to that forward-backward recursion to get the mass matrix. Okay, so is there a better way? In fact, that cost will go up, right? If you have a 10-link manipulator, it will probably be more than 10 milliseconds. It'll probably be 15 milliseconds.